All right, in this video, I'm talking about curvature in a Cal 3 sense, or a multivariable calculus sense. And so I'm going to start with this curve over here. You can envision this being a plane curve or a space curve. I don't really care. I'd say probably space curve because that's what we've been talking about today. And you can see that, if you were to just look here, it's not very curved, right? It looks mostly like a line. Whereas over here, it's curving a lot. Okay? And that's, kind of the level we're at as far as quantifying how curved something is. But I really do want to point out that this is a measurement of how unlinear something is, right? And so what we're going to do is we're going to define curvature, and I'm going to show you a couple of ways to compute it. I'm going to show you a really nice way of computing the circle, the curvature of a given circle, and then I will connect it back to the geometry of the curvature. So what I'm going to start by defining curvature. The curvature, which we use like a kappa or something, it's a kappa, but it's just, kind of like a fancy K or something. That is equal to the length of dt ds, where s is the arc length parameter. Now, we have not talked about reparametrizing a curve with respect to arc length, but it's something that you can read up on. Really, it's measuring how much is the tangent vector changing when I bump up, when I go this far along the curve. Which actually, if you think about curvature, that makes sense. Like, how much is my direction changing when I go, a little bit of distance? And that's the reason why you would want to, in this situation, reparameterize with respect to arc length, because a little bit of distance can either be a little bit of time or a whole lot of time, depending on, if it's parameterized with respect to time, how fast the thing's moving. So, but this is not going, actually getting this, you would need your curve already parameterized with respect to arc length, or you would need to go and do it. And we find that to be a little annoying. So we try not to do that as much as possible in this class. But one thing I do want to point out is that this is also kind of an issue of perspective. That if you take two circles, and maybe I'll just draw you two circles. And you are like one ant crawling around the edge of the circle. Well, this one's going to feel more curved than that. But we know in a certain sense it's up to, yeah, it's perspective or how big you are or something like that, or just, your notion of size anyway. So there's some strange things happening here. And definitely more to this than what we're going to do in this class. But basically, this is the definition, and this is like what makes sense. And from that, you can derive this. And so this is going to be a theorem, and I'm not going to prove it for you, but I'm going to give you the formula for curvature. So curvature is equal to, the derivative of t divided by the derivative of r, their respective lengths, the ratio of their lengths. And of course, if you're interested in why this is true, you could ask me and I could go through it with you, or you could just search YouTube. And there's a number of good proofs out there. I would be doing the exact same thing as them. But it's also equal to, and this is the one I tend to remember, it's r prime crossed r double prime divided by the length of r prime to the third. So it's like 1, 2, 3. So it's r prime crossed with r double prime's length divided by r prime taken to the third power. And I believe I used to, in this class, prove this formula, but I just don't think that it's going to be the best use of our time today. And what I'm going to do, the example I'm going to do is I'm going to just take a circle of radius A and show you that we can, if we just know what the radius of the circle is, we can know what the curvature is at any given time. So consider the circle, and with no loss of generality, I'm going to center it at the origin with radius A. And so I can call that, if there's one thing that we really learned in pre-cal is that I can parameterize this thing A cosine t, A sine t. And, I hope you'll excuse me for going into the into the realm of plane curves for this one. It's just going to make the computation much easier. Okay, so I'm going to actually use this, this first formula here. I'm going to say that, okay, well, r prime is equal to negative a sine t and a cosine t. And what would the length of r prime be? I don't know if you can see it. It's going to be a, because of the same cosine squared plus sine squared thing that I keep running into today for some reason. And so, yeah, the length of r prime is constantly equal to a, always equal to a. And as a result, I can say that t of t is going to be, it's r prime divided by the length of r prime. Well, that's negative sine t and positive cosine t, because I took r prime and I divided it by a, because that's the length. And just making sure that no, that's right. I need to take the derivative of t, which is derivative of negative sine is negative cosine, and derivative of cosine is negative sine. And the length of t prime is always equal to 1, right? Because it's a unit circle. It's going to be traced out in a weird way, but I'm going to say that the length of t prime is always equal to 1. And I really want the ratio of t prime to r prime. Okay, well, there it is. T prime over r prime is 1 over a. So that means that curvature is length of t prime divided by the length of r prime, which is 1 over a. And that makes sense, though, because the bigger the circle is, the less curved it is, right? If you took a really huge circle and looked at just a little bit, it looks kind of like a straight line. You think about, I don't know. Oh, some people get fooled by this, right? You look out on the horizon, and it looks pretty straight, right? But that does not mean that you are looking at a straight line. You're looking at part of a curve. And I think that's, oh no, that is not all I have to say about that, okay? I'm talking about the osculating circle, okay? Which, honestly, this isn't going to help you compute any of the, or solve any of the problems in this class, but it will give you a little bit of perspective. So you know how I was saying that here we have less curvature than, say, right here. And you're very familiar with the concept of a tangent line, and then, you know, last year in Cal BC, I convinced you of the possibility of a tangent-ish polynomial, right? Taylor series, Taylor polynomial. Yeah, we can lay in a polynomial that fits just right. I'm going to lay in a circle right here, and I'm going to tell you it's going to have to share the point, and it's going to have kind of this, basically the definition is it has the same curvature. But you get the idea of laying in a circle that fits just right on a part of curve. And the curvature is the reciprocal of the radius of the osculating circle. Okay? Because they say they share the same curvature, and the curvature of the circle is 1 over the radius. That means if for some reason you could calculate the radius of the osculating circle, then you would know what the curvature of the curve was. But, you know, that's kind of putting the cart before the horse. I will, you know, just to point it out to you, it was pretty decent. But this has got a big radius, less curvature, small radius, more curvature. That's all I got to say about curvature. Good luck. Just do a bunch of the problems, and you'll see that it pretty much works the same way every time.